In this LearnElectrics video, we take a look at calculating voltage drop in cables and also the resistance of cables in circuits. These are not the same thing, even though they have several things in common and each has its own special place in our work. These types of questions will always come up in the electrical exams and in the inspection and test assessments. You need to know them. We've had several questions posted to us where a little confusion has existed over which formula to use and which table to use. Get them the wrong way round and the answers will be wrong. We are asked, what are the formulas? How do I calculate voltage drop? Which tables do I use? And so many more. We begin with the resistance formula and calculating R1 plus R2 and which tables to use. Next, we look at the voltage drop formula and the relevant tables for this. Then, we will show each formula in use with guided questions and answers. And we will show you how to rearrange the formula and work the calculation backwards. Each question is fully worked out for you, and we show you where in the tables to find the help that you need. Begin with looking at resistance calculations and finding R1 plus R2 for radial circuits. It's important that you understand this next bit. Resistance and R1 plus R2 are calculated with the line and CPC conductors. We are anticipating the resistance of the cables if there is a fault on the circuit. A fault between line and CPC, nothing to do with the neutral. If we know the resistance, we can calculate the fault current that might flow. First of all, understand that as the circuit length increases, the conductor resistances will increase, shown here in this simple drawing. To calculate conductor resistance, we need to refer to table B1 in guidance note 3 or to table I1 in the on-site guide. The first entry here shows that 1 square millimetre copper conductor has a resistance of 18.1 milliohms per metre length, where milliohms is 1,000th of an ohm. This is what the resistance will be, say, from the consumer unit to the point of use, just one way. The second entry shows two conductors, from the consumer unit to the point of use and back again. This is now double the length as we would expect, and the resistance value has doubled to 36.2 milliohms per metre. Although the table states line conductor and protective conductor, the table can of course be used for calculating resistance values of any conductors if we know their individual size or CSA. This is the formula to use and is really very easy. R1 plus R2 for any simple radial circuit is the same as the resistances shown in the table. The table below the formula shows what each of the symbols mean. Pause the video and understand their meanings. What things will affect the R1 plus R2 or resistance? Smaller cable sizes or longer lengths will make the resistance increase, as will any increase in conductor temperature. This is one reason that we like to keep cables cool. A reduction in R1 plus R2 will result if the conductor CSA is increased, bigger cables, or the length is made shorter, and reducing the temperature of the conductors will have a slight impact. It will show as a slight reduction in the resistance. Now we can look at voltage drop and the relevant calculation and tables. Voltage drop is calculated along the line and neutral conductors. How much voltage is lost in the cable? We are looking at a fault-free circuit here, so the CPC or earth is not part of the calculation. Voltage drop will increase as the length of the conductors increases. Perhaps 2 volts shown here for a shorter circuit and 4 volts for the longer circuit. For the top drawing, in a 230 volt circuit, This means that 228 volts is available at the lamp. The bottom drawing, the longer circuit, has only 226 volts available at the point of use. To calculate voltage drop, we need to use the tables in Appendix 4 of the Wiring Regulations book. We will assume twin and earth cable for this video, and we should refer to table 4D5 on page 456. On the left, in the blue box, are the cable sizes, the cross-sectional areas for the popular sizes. The red box on the right shows the corresponding voltage drop as millivolts per amp per meter length. Notice that the MVAM number decreases as the conductor size increases. Each conductor or cable type will have their own set of tables within the regulations. We will need something to compare the results to, and this is table 4AB on page 430. It tells us the maximum voltage drop permitted as a percentage of the supply voltage. For a nominal supply voltage of 230 volts, 3% equates to 6.9 volts, and 5% is 11.5 volts. A voltage drop in excess of these figures is considered unacceptable. Here is the actual equation. Pause the video for a minute or two and become familiar with what the symbols actually mean. We should consider what affects the voltage drop. Smaller conductor size, bigger design currents, and longer lengths will all increase the voltage drop. In other words, make it worse. Having a larger CSA, a smaller IB or design current, and a shorter length will all improve things and reduce the voltage drop. So, let's have some questions on calculating cable resistances and R1 plus R2. Remember that we are only interested in the line and CPC conductors for this question. Question 1 asks, a lighting circuit is installed using 1.5 by 1 square millimeter twin and earth cable. If the circuit is 25 meters in length, what resistance is R1 plus R2? 4 possible answer choices are offered. Choose the correct one. This is a resistance question, so use table B1 in guidance note 3 or table I1 in the on-site guide. I've also included the formula to help you on your way. Pause the video and attempt the calculation, and the worked answer is on the next slides. We are calculating the resistance for a radial circuit or any two conductors that are not in a ring. If it helps, make a small sketch of the circuit to give you a visual aid. Table B1 is shown here. Find the cable sizes 1.5 and 1 mm for this question. This tells us that the combined resistance is 30.2 milliohms per meter length. This is the data entered into the formula. Take a moment to make sure you understand where the numbers have come from. We look at the calculation through and we have 755 on the top row divided by 1000 on the bottom row. Our answer then is 0.755 ohms for R1 plus R2, and we should choose answer C. Question 2 is also about resistances, but this time we will work the question backwards. We are still only interested in the line and CPC conductors. The question tells us that a lighting circuit is wired in 1.5 by 1 square millimeter twin and earth cable, and that R1 plus R2 is measured at 1.359 ohms. We must calculate the circuit length. We have deliberately made the circuit length and R1 plus R2 different to the last question. In this question, we must rearrange the previous formula so that the length is the subject. We will still use table B1 or table I1 for resistance values. First, we must find the resistance value of just 1 meter of cable. The question tells us that this is 1.5 by 1 mm cable, and the table shows this as 30.2 milliohms per meter. Now transpose or rearrange the resistance formula. Length is now the subject. We can use R1 plus R2 from the question and the milliohms that we have just found in table B1. So let's enter the data. Putting the numbers into the formula, we have 1359 on the top divided by 30.2 on the bottom. Our circuit length is 45 meters and our answer choice is D. Moving on to question 3 and voltage drop. Now we are interested in the line and neutral conductors, as this is where the voltage drop will show in the circuit. Remember that this is a fault-free circuit, and as such the CPC or earth is not part of the calculation. A single-phase heater circuit has a design current or IB of 8 amps and is installed using 2.5 by 1.5 square millimeter twin earth cable with a length of 15 meters. We must calculate the voltage drop for this circuit at full load. Now we must use a different table. We use the table that shows the voltage drop for the type of cable, which is twin and earth here. This will be table 4D5 on page 456 of the Brown Wiring Regulations book. This is table 4D5 and is specifically for flat profile cable with copper conductors, or twin and earth as we often call it. The question tells us that the line conductor and the neutral are 2.5 square millimeters. So find 2.5 on the left, trace it along the table to the right, and we have the voltage drop column. This tells us the millivolts per amp per meter that will be lost in this size of cable. In this case, 18 millivolts for every amp that flows through every meter of cable. Here's the formula. Pause the video and understand what each symbol is telling us. Enter the millivolts from the table, the 8 amps and 15 meters that have come from the question. The voltage drop for this question is 2.16 volts, and answer A is our choice. Question 4 will look at voltage drop in a lighting circuit, and now we'll compare the results to a reference table found in the Wiring Regulations book. Question 4 asks, a 230 volt single phase lighting circuit is supplied from a public low voltage supply and has a design current or IB of 4 amps. It is wired in 1 by 1 twin and earth cable and has a length of 45 meters. Calculate the voltage drop for the circuit and compare your answer to table 4AB on page 430. This is a typical exam style question. You will not be expected to calculate distributed lighting loads for the 18th edition or inspection and test exams and assessments. What is table 4AB? Go to page 430 in the Brown Wiring Regs book. It tells us the voltage drop limits. We are interested in the top row. Most of our work will be on low voltage public supplies from the national grid, where lighting only circuits have a limit of 3% and all other circuits, sometimes called power circuits, have a voltage drop limit of 5%. The table at the bottom shows what these percentages mean in real volts for a typical domestic circuit with a nominal voltage of 230 volts. The voltage drop must not exceed 6.9 volts for lighting and 11.5 volts for all other circuits. Let's now find the millivolts per amp per meter figure for 1 mm cable. Table 4D5 shows this as 44. We now have all the data that we need for the formula. IB is 4 amps and the length is 45 meters, both obtained from the question. This is the formula. Enter the data into the formula and the result should be 7.92 volts. Now we must compare this to the maximum voltage drop table. The table shows that for lighting, the maximum voltage drop should not exceed 6.9 volts. We have 7.92 volts, which is clearly unacceptable. So choose answer B. Let's look now at voltage drop in a shower circuit. Question number 5. A 230 volt single phase 9 kilowatt shower is installed using 10 by 4 square millimeter twin and earth cable with a circuit length of 20 meters. What is the actual voltage drop? To begin, calculate the amps from the watts. Then calculate the actual voltage drop. You will need to use table 4D5 on page 456. Pause the video, choose your answer. I like to draw a quick data table of what I need to know in order to answer the question. From table 4D5 we can see that 10mm conductor has a millivolt drop of 4.4. The length is given in the question, and we can calculate IB from information given in the question. Let's do that. Amps is watts divided by volts. 9 kilowatts is 9,000 watts, and the question tells us to use 230 volts. IB is therefore 39.13 amps, and we can now put this into our data table. We now have all the data for the calculation. The voltage drop for this shower circuit is 3.443 volts, and we should choose answer D. And on to question 6. This is about voltage drop in a heater circuit and will involve some extra calculations just for practice. If you can do these, you'll have no problems in the exam. A 240 volt single phase radial circuit in 2.5 by 1.5 square millimeter twin and earth cable supplies a 3 kilowatt heater. The circuit R1 plus R2 has been measured at 0.38 ohms. What is the actual voltage drop for this circuit? We need to make some other calculations before we can make a voltage drop calculation. If you wish, pause the video and attempt the question before looking at our method on the following slides. These are the key pieces of information from the question. Break this down into steps. Step 1. Write down what we need to know to make a voltage drop calculation. Then, step 2. Write down what we already know from the question, which is quite a lot. Next, step 3. Calculate the circuit length. Step 4. Calculate IB, the design current. And then, finally, step 5. Calculate the actual voltage drop. These are the formulas that we will be using. Make sure that you are familiar with them before the exams. Pause the video and understand what each one is used for. Step 3 is calculating the circuit length. In the green box on the left, we've found the resistance value of 2.5 and 1.5 conductor from table B1. This is 19.51 milliohms per meter length. Make the calculation as shown and we have a result. The length is 19.477 meters. This can now go into our data table. Move on. Step 4. Calculate IB, the amps. 3 kilowatts is the same as 3000 watts, and the question tells us that the voltage to use is 240 volts. So IB is 3000 divided by 240, and we have 12.5 amps. This can go into the data table too. Step 5. Go to table 4D5 and find the MVAM number for 2.5 square millimeter copper conductor. This is 18, and now we can calculate the actual voltage drop. Putting the numbers into the calculator, we have a voltage drop of 4.382 volts, and we can round this to 4.38 volts. And now we can choose an answer. The correct answer is D, 4.38 volts. This last question intentionally included several interim steps to show you that there will always be a way to find the answer, and the question will always give enough information for you to use. These are the formulas that were used in this video. Make sure that you are confident with the different formulas before your exam. Practice is key. Watch the video again, write the formulas down, make your own practice questions. It is better to practice a little every day than to try and cram all your learning into the week of the exams. Start now and keep adding to your mental toolbox. We hope you've enjoyed the video and we thank you for watching. It really is appreciated. Please subscribe to our channel to get access to all of our videos, and remember to click on notify to be sure of not missing our next video. And you will find even more information, videos and help on our website at LearnElectrics.com. And don't forget, you can also type in LearnElectrics, all one word, into the YouTube search bar to go directly to our channel at any time from any computer. We are constantly adding new videos to our channel, so don't miss the next one. And once again, thank you for watching, and we hope to see you again very soon.